looking at Leetcode number 543, diameter of a binary tree. It's definitely more on the medium side than the easy side. You know, they list it as an easy, but I would definitely say this is more of an easy medium. So here we're given a root of a binary tree. We want to return the length of the diameter of the tree. And the diameter of the binary tree is the length of the longest path between any two nodes in a tree. And this is really important. The path may or may not pass through the root. Okay? The length of the path between two nodes is represented by the number of edges between them. So here we can see there's one edge here, and one edge here. So our path is 1, 2, 3 is going to be our longest path. It's from here to here, or it can be from here to here. Okay, and then if our tree is 1 and 2, then there's just one edge and we return 1. Okay, so let's take a look at this. So we're going to have to create a recursive function for this, and when we're thinking about a recursive function, we have to think about the base case. All right. We also want to think depth first search because we want to get the diameter, so we want to get the maximum height on the left and the maximum height on the right. And so that's going to automatically, we want to think depth first search traversal when we're thinking of the height. So let's take a look at our base case here. Here we're at 4, right? If we get to the leaf level, what does that mean? Well, if we go to the left or the right, it's going to be 0, right? The diameter is going to be 0. There's no edges there. So we can return 0 if we get to a null value, all right? And now what we want to do at this level is we want to check what is the maximum on the left or what is the maximum on the right. We want to take the maximum between those two values, on the left tree or the right tree. You just want to pick one which is bigger, okay? Here they're the same, so we're just going to take that 0, and then we're going to add whatever the edge is or whatever the diameter is at that particular node, which is going to be 1. So we're going to send back 1 up the tree. Okay. Here the same thing. This is going to be 0 and 0. We backtrack 0, return 0 on both sides, and now we take the maximum of those two, of the left and the right, which is going to be 0, and then we add the current, which is 1. Okay, so then we return back up 1 up the tree. Now we get to this node here, and we want to take the maximum between the left and the right, which is 1. They're the same, and then add the current. So we're going to do 1 plus 1, and then send that back up the tree. Okay, here it'll be 0 and 0. We pass back 0, we pass back 0, take the maximum of those two and add the current, which will be 0 plus 1, and then we send 1 back up the tree. And here we get to the root, and we want to take the maximum out of these two. So we have 2 and 1. We're going to take 2 and then add the current. So we're going to get 2 plus 1, which will then equal 3, and that's going to be the diameter at our root node. Now this works if we're just trying to find the diameter from the root. The issue here is we need to find the diameter, the largest diameter at any node, okay, at any node. And so when that's the case, let me clear some of this out here. We have to think about this a little bit differently. Okay, so let's say we have a tree here, okay, at this 4, and I'm going to use a different color here, and I have 1, 2, 3, and 4 nodes here, and then I have 1, 2, 3, 4, and 5 nodes here. Okay, so now I have to look at what is the diameter here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, right? The diameter here is going to be 9. But what is the diameter of this tree here? Okay, this is going to be 1, 2, 3, 4, 5, 6, 7, right? So the longest path here is actually 9. It's this blue one, right? And so what we want to do to account for this is we want to keep a global max. And we can just set it to 0. And what we want to do is every time we get to this a root node, or a node, any node for that matter, we want to check what is the current what is the current diameter Okay, and if the current diameter is larger than whatever's in the global max, then what we want to do is max is going to equal current diameter. Okay, so here our current diameter is going to be 9. Okay, but then we're going to take the maximum of the left or the right and then pass that back up the tree. So our current diameter here is actually going to be 6. And so even though we get here, we're not in this node anymore, our max will not be updated. It's going to be set to 9 when it gets to this node, and then when it comes back up to the root, it's 6, so we're not going to be changing the max. And then we break out of our inner function, and then in our main function, we return the max, the 9. Okay. This is really sloppy. Let me just clean up my handwriting a little bit. Okay, we're going to return that 9. Now let's think about time and space complexity for this. We're going to have to go through every single node because we have to check at the leaf level of every part of the tree. So we're going to have to traverse through this entire tree. Okay, so our time complexity here is going to be O of n, because there's no way to solve this without traversing through every single node. At the leaf level, we're not doing any scans, we're not doing any linear operations. All we're checking is a max, whatever the current is. We're just doing a comparison, which is a constant time operation. So our real time is really just traversing through this tree. So it's going to be O of n. Now our space complexity. This is going to be for the height of the tree. Okay, and the height of the tree, if our tree is balanced, is log n. However, we're not guaranteed we're going to get a balanced binary tree. So if we're not given a balanced binary tree, the tree could, worst case, just be a one-sided tree. It could just all go left. And so if that's the case, the height is also going to be n, okay? Which means that our space complexity, the amount of calls we're going to have on the call stack for every single level here, is going to be the height of the tree, which at worst case will be the entire tree, which could be n. So our space complexity is also going to be O of n. Okay, so that's the idea behind it. Let's go ahead and jump into the code. Let me just disconnect out of here, over here. Okay, so here, what do we want to do? First, what we want to do is we want to go ahead and account for the edge case that we get an empty tree, okay, an empty root. So we can say if root is null, then we just return 0. Okay, the tree is the diameter is 0. Now what we want is we want to initialize a max variable and set it to 0, and we want a helper function for depth first search that takes in a node, and that's all it has to take in. Okay, and now what we want to do is we want to check, are we at a leaf? Okay, are we at a leaf level here? Let me just create a little more space here so we can see. And actually we want to check if it's null, if we have gone past the leaf. So we want to say if node is null, then we just return 0. Okay, similar to here, if we get to the bottom here, and then we're checking this space right here, like the left of the leaf, then we just want to return 0. That's what we're going to be returning at that point. Okay, and now what do we want to do? We want to get the left, whatever the value is from the left side of the tree. So we can say let left equals depth first search node.left, and then we want to get the right side of the tree, which is let right equal depth first search node.right. Okay, and now what do we want to do? We want to get whatever the left and the right is, that's going to be our diameter, and we want to compare it to whatever is in the max. Okay, so we want to say max is going to equal math.max of left plus right and whatever's currently in the max. Okay, and then what do we want to return? We want to return the max of left or right, and then +1 for the current level that we're at. Okay, and then we just call depth first search on our root and then return our max. Okay, let's go ahead and run that, make sure everything works. And we're good. Okay, so that's the idea behind it. It's definitely on the more medium side because, you know, I feel like if we were just doing the diameter of the binary tree through the root, you could call this an easy. But because we have to figure out the diameter from any part of the root, you know, you have to create this global max and account for that. And that, I feel like, definitely bumps it up in more of the medium category. But just think through it, you know, go through it step by step. And once you kind of think about it, it does start making a lot more sense. Okay, so that is Leetcode 543, diameter of a binary tree. Hope you enjoyed it, and I'll see you all on the next one.